Higher Notes, Unit 1, Section 7, the Expanding Universe. And this is part 3, where we look at the consequences of Hubble's law and then radiation from stars. Well, firstly, the consequences of Hubble's law. Well, as you now know, Hubble's law told us that if you plotted the distance to a distant galaxy on the x-axis and its rotational velocity on the y, you got a straight line, direct proportion relationship. So the further away the galaxy was, the faster it was receding from us. And Hubble gathered some really conclusive data which showed us this was clearly the case. There had been some speculation about it before him, but if you go back into the earlier 19th century, we thought at that time that the universe was probably just the way it was. Everything was staying pretty much in a fixed position. So this was really quite radical confirmation of the fact that the universe wasn't just staying still, it wasn't just staying the same, it was changing and expanding quite dramatically. So it was a big change in cosmology. But that led to some interesting consequences. Well, the first consequence, of course, is that we now knew with certainty that the universe was expanding. So that's number one. The universe is expanding. So you can say that the universe is expanding. The galaxies themselves are not expanding. The galaxies are moving apart, no matter which direction you look in. So be careful not to say the galaxies are expanding. The galaxy's size is essentially remaining more or less constant, but it's the universe itself that is expanding. And the second big consequence of Hubble's law is we can, as a result of it, estimate the age of the universe. And that had never been able to have been done with any accuracy before. So how did that come about? Well, if you imagine all of these galaxies, no matter where you look, right, they're all expanding, right? So they're all going away from us. Say we are on Earth here. Wherever we look, the galaxies are expanding. Now, Earth isn't favoured in any way. It wouldn't matter where you were in the universe. Wherever you looked, up, down, left, right, front, back, in all directions, the galaxies would always be moving away from each other. So I'm going to remove the Earth, although this is where we are, obviously, because this would be the case anywhere you observed the universe. Now, what Hubble then said was, if we go back in time, then obviously the galaxies would be a little bit sort of less far away from each other. So maybe sort of somewhere, let's get the same colour. So maybe this one would be kind of in there, that one would be in there, that one would be there, and so on and so forth. So basically, going back in time, these dotted lines, oops, forgot to draw that one in, the galaxies are all closer together than they were before going back in time. Now, if we keep pushing that process to its logical conclusion, then if we go back far enough in time, there will come a point where all of the galaxies would basically have been in the same position. This red blob that I've got there. So they all must have come from the same point at some point in the very distant past. Now, because Hubble knew how fast galaxies were moving with distance, he could gradually imagine how long that process took using his data. And we reckon it takes about 13.8 billion years. So this event in space and time from which all the galaxies came, everything that exists came, as you now know, is called the Big Bang. Sort of nickname, really. That's the red bit in the middle. And that Big Bang, we reckon, took place about 13.8 billion years ago. So the age of the universe is estimated to be 13.8 billion years old. So 13.8 billion years ago, we believe that all matter and energy in the universe came from a point, in fact a singularity, and we do not understand how that happened, or even whether we can describe it in any meaningful way at all, to be honest, because the laws of physics break down at the Big Bang. But nonetheless, Hubble's research and Hubble's evidence gave us direct evidence that the universe is expanding and led us to estimate the age of the universe at 13.8 billion years old. Okay, we now go on to part B, radiation from stars, stellar radiation. Well, let's imagine we have a star. You can imagine the sun, for example, as being that star. It's a big sphere of ionized gas. It's very, very hot. And it's giving off all sorts of different types of radiation, electromagnetic radiation that is, in all directions. Now, of course, the ones we are most familiar with in everyday life are the visible light. So we've got visible involved. But we've also got infrared. We feel warmth. We've also got ultraviolet. Those are the ones that we're most directly able to detect, because that can tan you, for example. The infrared makes you feel warm. But in fact, there are other wavelengths as well. We can even get into the X-ray region. But the point is that there is a spread of wavelengths coming off. So there's a spread of wavelengths being emitted by all stars. They don't just emit at one wavelength. Otherwise, of course, the sun wouldn't give us white light. The very fact that it's giving us white light is because the visible itself, of course, can be further subdivided into a whole range of colours red, orange, yellow, green, blue, indigo and violet. So we've got this spread of wavelengths, fairly wide range. Now the way the spread goes though is not uniform. It turns out that if we plot a graph of the sort of energy density, sort of energy given off per square meter per second effectively against the wavelength, you see that you don't get the same amount of energy at all wavelengths. So what we're going to do is on this y-axis, we'll plot the wavelength in nanometers of the emitted waves, and on the y-axis will effectively be the energy given off by the particular wavelength of that wave. Right, well the first thing then is that we get something like this sort of going on. Let's just see now if I can sketch this as accurately as I can. So a typical curve would be something like this. Now as you can see, it's not symmetrical. It sort of takes longer to reach the x-axis on the right hand side of the graph than it does on the left. It's more steep on the left if you like, and less steep on the right. And it also peaks at a particular wavelength as well. So those are the two sort of features of it. It peaks. Now if we look at the peak here, we can identify the particular wavelength, lambda peak, at which the particular star we're talking about emits. I'm just going to move my axis down here a wee bit. So that's lambda in nanometers. So it is emitting over quite a wide range of wavelengths, but it gives off more energy at one specific wavelength. And this is the pattern for all stars. Now the other thing that we've discovered is that this particular spread of wavelengths corresponds to a star of a particular temperature. So for example, I would like this one to be a temperature at its surface of 5,500 Kelvin. That's the surface temperature. Okay. Now interestingly, if we go to a cooler star, so let's say maybe 4,500 Kelvin, let's say something like that, it would have a curve something like this. Now, a couple of things to observe there. Well, this new curve is for a cooler star. That's cooler on the surface, 4,500 Kelvin. The temperatures at the core of the star are over 1,000,000 Kelvin. These are the surface temperatures. Now, if you look carefully, you'll see that the peak of this one has a different value. So lambda peak, I'll do a wee arrow around there to show you that. So this is lambda peak. I'll call it lambda dash, and I'll call that T dash just so that you know it responds to the different one. So the peak is shifted a little bit to the right when the temperature goes down. So when the temperature at the surface of the star is different from another star, the curve has the same general shape, but the peak shifts to the right and it's not as high. It's not giving off as much energy per square meter per second, essentially. So you can see that a cooler star doesn't give off as much energy in general as a hotter star, and its general wavelength profile is shifted to the right. Okay, now we're talking probably at about sort of 500 nanometers there. This is only approximate, of course, and you're probably getting to about maybe sort of 700 nanometers in here. Okay, these are very, very rough approximations. So you can see then that the cooler stars generally emit more in the longer wavelengths. They're sort of generally redder than the kind of bluer stars. So you tend to think then that you tend to know that blue stars are sort of cooler. I beg your pardon, blue stars are hotter than red stars. Okay, so you can see that the bigger wavelengths, which is near the red end, corresponding to the 4500 K1, a bit cooler of a star than that, whereas the blue one is the hotter. So it's the opposite way round from the taps on a washhand basin, for example. So I could plot many more lines on this graph, and gradually as you increase the temperature, the pattern is followed. As you increase the temperature, the peak gets higher and the wavelength of the peak shifts to the left. Okay, so to put that into words, all stars have a distribution of emitted electromagnetic energy spread over a wide range of wavelengths. So that's the first point. The surface temperature of the star determines two things. The peak wavelength of emission in nanometers, and two, the amount of energy emitted at that peak wavelength. So the temperature at the surface of the star is very important for determining the actual wavelength in nanometers of the peak in the graph, and how tall the peak is. That is the amount of energy actually given off by the star at that wavelength. Okay. So the peak wavelength then lambda peak is shorter That's a smaller wavelength for hotter objects or hotter stars than cooler stars. I'm really just here putting into words what the graph shows. The peak wavelength, lambda peak, is shorter for hotter stars than cooler stars. And if you go back up to the graph, you can see that there's lambda peak there for that fairly hot star, a relatively hot star, 5,500 Kelvin. It's actually kind of a middling star, really. That's about the temperature of the sun at the surface. But if you go to a cooler star, temperature at the surface 4,500, then its wavelength of peak is about 700, so it's a bigger wavelength. Okay, so cooler stars emit at bigger wavelengths. And then finally, it turns out then that the hotter the star is, the more radiation energy it emits per square meter. At all wavelengths, compared to a cooler star. The hotter the star is, the more radiation energy it emits per square meter at all wavelengths compared to a cooler star. And again, I'm just putting into words what the graph tells you. As you can see, the hotter star is emitting more energy at all wavelengths. In other words, the curve is higher up the y-axis at all wavelengths than the cooler star, and that's the shape it takes, that asymmetrical characteristic shape. And finally, it is the radiation peaks shown above which, oops, don't know what that's doing there, which allow the temperature of stars to be measured. So if you've ever wondered how we know what the surface temperature of the sun is, we know it's around about, what, 5,800 Kelvin. How do we know that? Because when we observe all the radiation coming off the sun, we plot this graph of the energy against the wavelength, and it peaks in such a way that it corresponds to a 5,500 K gas, and we can replicate that on Earth, you see, to confirm that. Right, now just to finish this section off then, we can use this knowledge of the radiation curves against wavelength for stars to say something about the universe, because we can observe distant stars in distant galaxies and compare them with closer ones. So what we can now say then is that the universe as a whole is cooling down as it expands. And there's something called cosmic background radiation, And this has proved to be quite really very important for helping us understand the cooling of the universe since the Big Bang. Obviously, at the Big Bang, we believe the temperature of the universe was extremely high, too high to actually understand at the moment, to be honest. But we now know it's considerably cooler, remarkably cooler, in fact. And this came about from a discovery in the 1960s, where, if we imagine the Earth, astronomers were observing in the microwave region, and they looked in a whole number of directions, and they found microwaves arriving at the Earth uniformly in all possible directions. So it didn't matter where they looked in the sky, they got a similar intensity of these microwaves. Now that was quite surprising. Uniformly detected in all directions. This was quite surprising, because normally in astronomy, when you detect radiation, it's coming from a particular source, a particular galaxy or a particular star. So when you move your detectors a couple of degrees to the right, the reading falls away, or a couple of degrees to the left, or a couple of degrees up or down. But we were getting a fairly uniform spread of these microwaves everywhere, absolutely everywhere we looked. Now, the only explanation for that was that these microwaves must have been created not long after the Big Bang itself. So their wavelength has been measured, and when you measure the wavelength, as you now know, of radiation, you've got your lambda, it tells you then what sort of temperature that corresponds to. And it turns out that it's called cosmic because it comes from all over the cosmos, and it's in the background all the time, this radiation. It turns out that the cosmic background radiation suggests a temperature of the universe is measured using cosmic background radiation to be about 2.7 Kelvin. Now 2.7 Kelvin is pretty cold. So the universe at the moment is really very, very cold. So we mean the universe as a whole, the sort of average, if you like. So we're not talking about the centre of stars where it's incredibly hot, but outside of them, the temperature is very, very cold, much colder than it would have been at the start of the universe, at the Big Bang. So to conclude then, the uniformity of the cosmic background radiation is very strong evidence that its origin lies right at the beginning of the universe itself, because it's so uniformly spread. If it had occurred much later, it would then have been more localized in a particular place, but it isn't, it's everywhere. So it started at one point and is spread out everywhere. And that brings us to the end of this part.